Assalamualaikum warahmatullahi ta'ala wabarakatuh. We are from group 14 and we got set 1 for the assignment. The first member is Muhammad Fidaus, the second one is me, the third one Maslah, and the last one Syafiqah Batrisha. So for my part, I will talk about abstract, introduction, and propose solution by adding generator. So the first one, abstract. This paper optimized economic dispatch on a 275 kV network with 4 buses, 3 generators, 2 large solar system, which is LSS, 6 transmission lines, and 4 loads. Economic dispatch is done within generator constraints and transmission line capacities. The network is tested with full and half loads. Both LSS produce different power. An external generator linked to bus 4 reduces transmission line strain when power limits are exceeded. Add a transmission line in parallel with the overloaded wires instead of a generator to bus 4. Next, introduction. Automatic management system, especially supervisory management and knowledge acquisition SCADA systems, are popular in chemical, organic compounds, oil refineries, steelworks, electricity generation facilities, and water sewage treatment plants. Measure, forecast, build, analyze, and plan with engineered SCADA systems. Network, distribution, and monolithic different SCADA configuration exists. The SCADA system controls remote workplace and systems. Economic dispatch schedules all market generating units in the installation to lower fuel prices and meet system limits, generating across committed units to meet constraints and reduce energy consumption is another way to describe it. To reduce operating costs, interconnected power system must discover each power station's entirely actual and reactive power schedule. Interactive Power Structure Package Powerworld Simulator. The colorful and graphical simulator performs engineering analysis and explains power system performance to non-technical audience. This simulator now has powerful new features and many smaller modifications. The software solves 250,000 buses electricity systems. These methods are needed for integrated economic dispatch, PTDF, area transaction economy analysis, contingency analysis, and short-circuit analysis. Colorful interfaces make all systems accessible. Simulation take minutes or seconds. Powerworld will analyze the electricity network for this assignment. 3 parts will be analyzed. 3 parts will analyze electricity. Firstly, electricity network simulation. Next, the simulation results are analyzed to evaluate whether transmission lines and generator operate within their capacity. And the last one, the final simulation requires a solution.
Okay, hello. So I'm going to show you how to do the economic load dispatch. So let's start with drawing the bus. Let's say I draw here. I want to make a circuit like this. So go to draw, network, click bus, and click here. And then let's say the bus is bus 6. Change your voltage according to your own assignment or your own set. Click down, and then you have that bus, small bus. Make it big. This also you can change the size. Now you have that bus. Now how to do the transmission line? It's easy. Go to transmission line. If you want to add from this bus to that bus, just one click and double click and click OK. So you go to parameters, input your maximum capacity of the kVA, MVA, and then go to geography, insert your line length, let's say 200 kilometers, and then click save. Go to parameters, calculate impedance, kilometers, yes, and then change your value here for your impedance per kilometers, and then click OK. So you have that. Now I'm just going to delete this because I don't need this. And then to show the percentage here, double click here and tick always show value, show percent value. Now you have transmission line and also the bus. Now how to do generator, go to draw network generator, click anywhere, click at the bus you want to put your generator, go to voltage and power, insert your minimum and maximum. The set point you can set any value, it will change according to your load. And then go to cost, go tick cubic cost model, insert your alpha, beta, and also gamma, and then click OK. Now if you want to insert the solar, the same thing, but the difference is if you want to insert the solar, go to display information, change the rotor shape, instead of dog bone change to solar, and then go to power and voltage control, insert your LSS value at the set point and also maximum, and insert your power factor, change this to constant power factor. Then for the cost, choose none and insert your value here at the variable, then click OK. Now to show the to insert the load, network, load, and then you will have this load. Click at the bus you want to put the load, and then insert your value P and Q here, and then click OK. Now to show the power flow, what is the power flowing through the line, go to field, go to transmission line field, click at the line and click OK. So you have that value flowing through the line. So if you want to show for the generator, go to field, generator field, click at the generator, tick the generator edge status and click OK. Now you can run your load flow, go to run mode, tools, and click play. So you can turn on or off your generator by clicking this box, and also you can turn on or turn on your transmission line by clicking this box. So now last thing, to show the field here, go to draw field, area field, click anywhere. It will if you want to show the total hourly cost, click total hourly cost. If you want to show the incremental cost, go to select a field, find OPF/lambda, and then click OK. So that's it for the methodology.
Hello, my name is Maslah. So we will continue with analyzing or performing the optimal and economic dispatch on the network. So in the network, basically it is divided into two main conditions. So one condition is when there is a full load connected to the network, and the second condition is when there is a 50% load connected to the system. And also in each case, we have two solar farms here. So we vary the output from those solar farms from 0, 50% to 100%. And we have all these conditions here stated. And so we want to test and perform the economic load dispatch and see how each case responds to the system, while at the same time ensuring that the generator's capacities in the lower limit and upper limits are not exceeded, and also the transmission line capacities are not violated. So let's first start with the full load condition. So in the full load condition, we can see that in here in generator 1, in all of the cases when there is a full load, the generator 1 is providing its maximum capacity, which is 300 megawatt, and generator 2 also operates at maximum capacity in all cases except in case 1 when we have an full output from LS or the solar farm 1. So here in this this solar farm can provide up to 100 megawatt. So when we have 100 megawatt following from this solar farm, we can see that generator 2 outputs 445 megawatt. And also in the other case, which we have one, also if we also take another 50, which is from this solar farm, which has capacity of 50 megawatt. Also, if we get 50 megawatt from here, we can see we get 415. But in all other cases, it is operating at its maximum capacity. Generator 3 has a generous limit of 700 megawatt, so it's always operating under its maximum capacity. And also it is operating higher than its limit, which is 25. So when we go to the hourly cost, so the hourly cost in our question, it's maximum when we have 50% output from solar farm 2. So if I turn off solar farm 2, and here when we have 50% output, we'll have here 52 ringgit per megawatt hour. So that will be our maximum. We will have the lowest when we have full output from both of the solar farms, and that will provide us an extra 150 megawatt. We will reduce our maximum, or how much cost that we have to pay per hour for per megawatt hour. So we can see it drops down all the way to 41.2. And when it comes to the transmission lines, so the transmission lines, transmission line 1, 2, 3, and 5, they are most of the cases they are overloaded. Transmission line 1 and 3, they are always overloaded. Transmission, there are cases where transmission line 2 is not overloaded, and that is when we have on this solar farm, when we have on a capacity that is less than 50%. So when it's on 50% or 0%, this transmission line becomes normal, operates at high capacity, but it's not overloaded. And also in this transmission line, when we have both farms operating at full capacity, then it becomes it operates normally. But in all other cases, it is overloaded. And this we will propose solution to overcome this, and will be proposed by my colleagues. But so now let's move on to the 50% capacity. So when we have 50% capacity, in all the cases, the system is operating under operating, or the generators are operating in a normal condition. They are not exceeding the lower limit, nor they violating the upper limit. Same for the transmission lines. So the system is operating in a good, stable condition. The highest cost incurs when we are not using or utilizing both of the farms. So if we are not using any of the solar farms, we will get a cost of 26.3 ringgit per megawatt hour. And we will have of course our lowest when we are using both the solar farms, and that will give us an extra 150 megawatt. And that is basically for the 50% load. There is no violation in the system. So now I will welcome my friends to propose two methods that we can solve when there is violation in the transmission lines are overloaded in our case. Thank you.
Okay, for the proposed solution, if we add the generator, first we take a look at the base circuit. Based on the base circuit, the output that we can see from the full load condition is overload. Compared to the half load condition, the system did not face any overload. So to prevent the overload happen, we add 375 megawatt at the bus 4. As we can see, the output from the full load condition was not overload. The total hourly costs were reduced similar with the incremental cost. Then the half load condition, when we add the generator, was also the same with the full load condition, where the total hourly costs were reduced similar with the incremental cost. Since the total load likewise lowers, it can be seen that the price for a 50% load is significantly less than the price for a full load. Thank you.
Assalamualaikum and hi, my name is Nur Shafika. So I will continue with the next proposed solution. From the previous video, one of the group member has explained about the proposed solution using the generators. So for this, another method is by adding transmission line that is parallel with the transmission line 1, 3 and 5. So as we can see here in the figure 3.3 and as well as with the simulation, the transmission line added with the transmission line 1, 3 and 5. So after we do the simulation, we tabulate the data for the full load condition and 50% load condition. So for the full load condition, we can see that the highest incremental cost is when 50% output from LSS2, and the lowest incremental cost is when full output from LSS1 and 2. For the 50% load condition, we can see that the highest incremental cost is no output from LSS1 and 2, and the lowest incremental cost is full output from LSS1 and 2. We can see that the difference between the lowest and the highest, which effect from the output of the LSS, because without both LSS, the generator will have to run at full capacity to power the system's demand. But when LSS1 and 2 are both completely utilized, it will be one of the factors in the price being significantly cheaper. So for this method too, by adding the transmission line, it is also possible to prevent the base circuit from overflowing. 3 transmission lines has been added parallel with the transmission line 1, 3 and 5, as you can see here in the circuit. So this is due to the fact that these 3 specific lines experience the largest overload. So the findings of the data in table 3.3 shows that since the total load also lowers, the overall price for the 50% load is significantly less than the price for a full load. When LSS1 and 2 do not produce any output, the cost is highest. Oppositely, when they produce all of their production, the cost is lowest. However, the only modification is the absence of the overload condition. So, 2 approaches to bypass the overflow circuit has been simulated, and both have proven successful in removing the overload condition and maintain the generator limitations. Furthermore, from all of the data of results, it can be observed that the method of adding additional generator at bus 4 is the best result compared to adding 3 new transmission lines and has a lower incremental price compared to the method 2. The total hourly cost and incremental cost for method 1 at half load conditions with full output from LSS1 and 2 are 24,547 for 8% and 14.39 ringgit megawatt per hour respectively. It is significantly less expensive than method 2, where the total hourly cost is 25,711 and 80 cents per hour, and the incremental cost is 25 ringgit 51 cents megawatt per hour. Additionally, adding the generator will cost less to implement than adding the 3 new transmission line, which will cost about 1 billion ringgit. As a result, installing generator makes the system more robust and allows for the best economic dispatch. Also, another recommended method which is adding a shunt capacitor. It is one of the most effective solution to lower the cost too. The nodes or load points where these shunt capacitors are connected, and its placement primary purpose is to operate as a reactive power source for voltage management, as well as increase the maximum power limit. Additionally, it can increase the stability of the system and lessen the lagging component of the circuit system. As for the conclusion, from the Powerworld simulation, it is observed that overall cost of the system that utilize LSS is reduced due to the LSS that also acts as generator supply power, which potentially lowers the output value of other generators. A full load system has a greater overall cost compared to the half load system. The system generator output is dependent on load demand. Furthermore, the generator output decrease as the total load reduce, which reduce the system's overall cost. Other than that, through two strategies that were shown in the simulation in order to resolve the transmission line violation, the methods are adding the generator to the network's bus 4 and adding transmission line in parallel with the overload line. From these applied methods, both methods able to solve the violation issues. However, in terms of cost, the first method yields a better result than the second, due to the fact that method 1 total hourly costs and incremental costs are substantially cheaper than method 2 when there is load and no LSS supply. According to logic, adding one generator will be less expensive than adding 3 transmission lines. So overall, we use the Powerworld simulator download from the Powerworld official website to complete this project, which also applies what we have learned in the power system control course throughout the process, with the exception of frequency control because Powerworld does not have this feature. So that's all from group 14. Thank you.